Have you ever thought how your phone unlocks just with your face, or how ChatGPT crafts human-like responses, or how Tesla cars would detect the stop signs? All this magic really starts with one fundamental concept: neural networks. In today's video, we're going to uncover the neural networks, how they really mimic the human brain in terms of how they learn, predict, or make decisions. I'll even show you how this connects directly with how ChatGPT works. In this video, we're going to talk about the neural networks, and the whole idea is the researchers wanted to mimic the human brain, how we learn with the help of these neurons. We wanted to understand that part of science, and this knowledge we used in terms of creating algorithms which are mathematical in nature, obviously, and mimic the behavior of the neurons. Let me show you how neuron really looks like. All right, this is a web of neurons, tons of neurons bundled together, and this I will denote as biological neuron. And we are going to mimic this behavior in terms of the artificial neuron. Let's learn how the neuron really works. It got inputs from the other neurons that are connected to it. In the center of this neuron, in the center of this tree structure, there's an excitement energy. For example, you are hurt or there's a heat incident. This neuron may or may not fire up. If the heat is too high, if you're burning, if you're putting your hand on oven, your neuron will fire up, send the signal to your brain. You got to stop doing this. So there's a threshold. If the energy exceeds, if the heat energy, if a cold energy, pain energy exceeds a certain threshold, this neuron fires up and sends an electrical signal. If it's normal day-to-day life, a little bit warm, a little bit cold, you're going to adapt to it. You're not going to fire up a neuron, like a pain signaling neuron that would kind of give your brain an information, you got to stop doing this, like a sudden information. This will not happen unless you exceed a certain threshold of pain. So this is what we're trying to achieve mathematically in our algorithms. So input from other neurons in the center of the neuron, when the cell exceeds excitement, when cell excitement exceeds the threshold, it fires up and sends electrical signals to other neuron. And that's how the process continues. Inputs can increase or decrease cell excitement. So a lot depends on inputs, a lot depends on how each neurons are connected, a lot depends on how they are programmed, how your childhood led to a certain level of programming. If you like a certain food in your childhood, you might end up liking the same kind of food rest of your life. If it does not match those requirements in your adulthood, you might start thinking, oh, this is not good. I dislike this. Your likes and dislikes are developed based on information that's stored in the neurons. So a lot of work is going on in these neurons. Now let's dive into how ChatGPT really works. They have something called transformers. Looked at text mining in our previous videos, which actually is the base layer of all these algorithms. When I say all these algorithms, I mean ChatGPT, Grok, Gemini, like the generator algorithms, which can generate text from their learning experience, from their knowledge, and give you some meaningful information. So they have mastered transformers. Google keep talking about this. They have been developing transformers. They were the one who actually initially gave transformers to OpenAI, and they made it public. So those transformers are the key to machine learning and text predictions. So these transformers are built with billions of neurons. Each neuron helps to predict the next most likely word in your sentence using everything it has learned from everything, tons of neurons connected to give you one single prediction. And that's how these learning algorithms work. For example, the skies model will predict. You probably mean the sky is blue. And that's what the work of neural network is. ChatGPT crafts human-like responses. It's simply neural network at scale. If you learn the basics in this video, you learn whole of ChatGPT. Just the basics though, right? All right. So we understood how biological neurons work, and we are going to now learn about how artificial neurons work. We understand that there's level of input that goes through uh, the center of the neuron. which fires or does not fire based on the excitement energy that it has received from the inputs. And if it exceeds the excitement energy threshold, electrical signal is sent to another layer of neurons or another level of neurons or the connected neurons. Let's see how we mimic this in mathematics. All right, we're going to use a loan prediction example. We have three independent variables: age, credit score, and the kid, how many kids you got. All right, so this is my independent variable 1, 2, and 3. And I got this prediction whether to give this person loan, yes or no. All right, input and output. If you have output of 2 that is binary in nature, we need to have binary output layer in our deep learning module. Let's see what I mean by that. So I got 3 inputs and I got 1 output. It could be binary 0 or 1. I'm not doing like fancy classification here. I got either 0 or 1, just one output layer. Input is the outermost layer, which mimics this neuron here. And we're talking about the final output. And for example, this is something called hidden layer. Some processing, some information processing is going on here. You could call it as brain. Right? Let's see what I'm trying to go after. So input layer, output layer, output layer needs to have just one node, which will either have two kind of predictions, either 0 or 1. All right. What are these inputs? We just looked at these inputs are age, credit score, and if you got any kids or not. So age, credit score, or if you got any kids or not. What are you going to do about this? We will create a hidden layer. When we talk about the neural networks, it's almost like the brain. That's my personal analogy of hidden layers because some processing is going on here. So why do I only have two nodes here, 1 and 2? I could create more. Let's say 3, 4, 5. I could have as many nodes as I want. Based on what? Based on how much learning I really want to achieve. But for this example, I'm going to stick with just two nodes. I'm going to not complicate it so that we are able to understand it better, the whole process. All right. So what happens with these nodes in the hidden layer? There's a network of information sharing that begins with the help of hidden layer. You got to have at least one layer, at least one hidden layer for it to be a neural network. Now, I create randomly assigned terms called biases. Bias 1, bias 2, and I associate that bias theta 1 to this first node and theta 2 to this second node. How did I create these biases? Completely random. No initial basis for this creation. And I associate a final bias to this final output layer that's theta 3. All right. Some books might put the bias separately as an input layer, but we are going to use this kind of analogy to show the biases right next to the hidden layer nodes or right next to the node that we are interested in. All right. Now, another concept is called the weights. These are randomly initiated weights 0.01, 0.024, 0.013, and I randomly initiated the biases 0.1. So this is my bias, and weight, and weight. All right. So I got two ideas, weights and biases, and I begin this algorithm by randomly assigning them. Now, how do these really work in making the prediction? So as you know, we have three input variables, age, credit score, and if you got kids or not. And if this person is going to get the loan or not, we're going to learn how this algorithm works. So the first step in this process of learning through neural networks is to standardize the data. What do we standardize? We standardize the input variables. What are our input variables? Age, credit score, and kids. Let's go back and see how they really looked in our data set. So here's how the data set looked. Age, credit score, and kids. Age was 30 and 45, credit score 750 and 800, and kids were 2 and 1. All right. So we don't use this directly. We convert them to standardized data set. Age becomes 1.08, credit score becomes 1.69. How did it become into these smaller numbers? It's based on the mean and standard deviation. So this is how much it's deviated from the standard deviation, 1.69, 0.75. And we have covered this extensively, how to standardize in our original first or second videos. All right. So we got the standardized data set, and I got age as 1.08, credit as 1.69, kids as 0.75. I got my weights. I got my biases. So how did I get these weights and biases? Completely random. Randomly assigned weights, randomly assigned biases. Zero point 0.1 and 0.2, and here 0.3. Now, this neural network algorithm, which is also called propagation algorithm, why it's called propagation algorithm, we're going to learn about it. Propagation algorithm, it uses this 1.08, multiplies it to the weight 0.01, and gets me a value here. 1.69 times weight, randomly initiated weight, gets me a value here. Kids 0.75 times weight 3 gets me a value here. I already have my bias term. I got the fourth value here. Adding all these up, summing them together, I plot that on the x scale of this chart. For example, all these add together to give me a value of 2. And I have chosen this S-shaped sigmoid function for my activation function. Now, this idea of activation function is same as creating a threshold. It's the same idea. If you have spike in your pain, your neurons are going to go to your brain sends a signal back, stay away, it's too painful. That's how the neurons work, and that's exactly what we learn from our biological neurons. And this is something acting like a threshold of pain. And we have chosen this threshold to be sigmoid function. If it's too large of a value, if the sum comes out to be too large of a value, example 800, my output, my pain output would always be 1. So it ranges from 1 to 0. And I got 0.5 in between. So whatever the number beyond 6 on the x-axis, I would always have 1 as my output. Let's say the sum comes out to be just 2, and I hit it here, and I turn this way, my output from the sigmoid function is going to be 0.8. Similarly, if my sum is really 0, my output would be 0.5. If my sum is negative, my output would still be, sorry, my output would be 0. If it's more than -6, my output would be 0. If it's -2, my output would be 0.25. And this is my prediction. Let's say the sum comes out to be 0.25, and sum from here, from this node, comes out to be 0.1. So 0.25 plus 0.1 plus the bias term that I randomly generated, they all add up to form 0.8, which is turned. So this 0.8 now has to go through another set of the same sigmoid function. So 0.8, I plot this 0.8. Since this 0.8 is not more than 6, so 0.8 would give me what? 0.8 is going to give me this term, which is just 0.6 something, roughly. Now this 0.8 is giving me 0.6, and I know from the trained data set that this is supposed to be 1. My propagation algorithm turns back, goes back, adjusts these biases and these weights, and also based on the importance factor, It tries to understand which of these input variables, credit, kids, or age, is contributing to faulty prediction, and which of these input variables is really helping with the correct prediction. So it goes back, updates the weights and biases, gives more importance to the input variables which are contributing more toward the weights and to the final correct prediction, and gives less importance to those who are contributing to the incorrect prediction. And finally, these weights and biases are locked down, they are frozen, and this is my neural network model that I can use to give a new person as an input. For example, a new guy from the trained, no, sorry, from the test data set, or completely random guy comes in. He has a certain age, let's say 25 years. He has a credit score of, let's say, 800, and he has no kids. Algorithm does its magic based on the frozen weights and biases and gives an output based on the learnings it has done on the existing data set, which is now frozen, and it gives an output of 1. Yes, this person you could give loan. And similarly, another person who may have 5 kids, an algorithm may say, you cannot give loan to this person. I mean, the prediction is 0, right? But the challenge comes when somebody asks us to explain why you did not give loan to this guy B. Well, how will you explain this? It's all in terms of weights and biases. What are you going to explain? You might want to explain based on, oh, layer 2 of my deep neural network, or the first hidden layer of my neural network had 0.25 as my bias and 0.50 as my weight. That is why, based on neuron 2, this person is not eligible for the loan. Well, that's not going to fly in the court of law. Nobody's going to buy your explanation. That's why we say neural network really produces a black box. This is basically a frozen black box that you cannot explain any information from. It's like input in, output out, right? You cannot explain this black box, at least in terms of the legal language, or at least logically, because all the information is now frozen based on weights and biases and node number of nodes you gave the algorithm, and based on certain fine tuning it has achieved to make those predictions based on the data set you really trained it on. That is why these algorithms like ChatGPT, Grok, Gemini would at the bottom put a disclaimer saying that we are not responsible for what it's generating. We have simply trained it based on the data we had, and what it's generating, it's completely up to the algorithm, its weights and biases, and we don't take that responsibility. What essentially they are saying is there are tons of weights and biases we don't understand. We cannot take that kind of liability. It may have an opinion on a certain topic, far right. It may have another algorithm may have on the same topic the opinion on the far left, and there could be a spectrum of opinions, and why it chose a certain opinion, it's completely up to that algorithm data trained on weights and biases and how people have interacted with that, with those algorithms, and how it learned. It's so many variables in the mix you cannot explain. That's why these algorithms are practically the black box algorithms, that you cannot explain their weights and biases, and that's the biggest limitation of the neural network. Moving on, I want to introduce another hidden layer. Right now, we have talked about just one hidden layer, but if I introduce one more layer, I would start calling them as deep neural network. You would have heard of this term, deep neural network, and that's what these algorithms for ChatGPT, Grok, Gemini would use. They will have multiple layers in the mix. For example, layer 1, layer 2, layer 3, and so on and so forth. You can define as many layers as you want. What's the advantage? You're slowing down, or you are expecting more from your computation power. You just don't want to do this layering unnecessarily because you're consuming a lot of computation power. Advantage is it improves the accuracy of your prediction, but disadvantage is you might be overlearning from the data that you cannot do a good job on the newer data. So this layering really becomes handy when we are talking about image processing. And we're going to look at those image processing using deep neural networks in our future videos. But the takeaway is even a single layer is good enough for a daily regression or a classification task. If you do not have any layer, so what I mean by that, no hidden layer, you're practically talking about logistic regression. So ex example is output weights 1, weight 2, and so on up to weight n. What would you do in logistic regression? You have an output, you would call that as y, and you have a bias term, that's beta 1. So in both the cases, I got a bias term. I got beta 1 plus w1 times uh, x plus w2 times x2, or I got a term here, like a constant term here, constant 2 here, constant 3 here, and constant n here. And this is my randomly generated weight. So beta 1 plus W1 times C1, W2 times C2, plus W3 times C3, and so on, and Wn times Cn. And that becomes practically a logistic regression algorithm if you do not have any hidden layer in it. If you got the hidden layer, I mean, if you have just one hidden layer defined in your algorithm, then you could use MLP classifier if your algorithm or if your prediction task is a classification like 0, 1, and 2, or sports, sports, vehicles, and uh, politics, like classification task. If you got a regression task, then you can use MLP regressor. So when we do not have a hidden layer, we call it perceptron. If you have one hidden layer, we call it multi-layer perceptron. And if you have more layers, obviously you would still call it as multi-layer perceptron. All these things, I mean, multi-layer perceptrons can be done through MLP classifier. And MLP classifier is obviously you need TensorFlow library, which is part of, sorry, TensorFlow has Keras library in it, and Keras makes this life easier when we're trying to define the multiple hidden layers in our algorithm. But if you don't have a hidden layer, practically you're talking about logistic regression, so you could use like basic algorithms like SGD classifier for that matter, and it's part of the scikit-learn package. All right. So when we're talking about the multi-class or multiple class as potential output, we got to use this function called softmax function. The purpose of the softmax function is to give you the probabilities associated with each class. For example, you got three classes to predict from: class A, class B, or class C. Let me give you an example. Class A may represent sports, B may represent news, C may represent politics. So it learns from all these columns and it tries to predict the output based on class A, B, or C. Now, it's going to give you the probability. All these columns for that given row is predicting class A, that is sports, with probability of 0.5. News, politics and uh, class B may have probability of 3 and zero point 0.2. So in other words, I'm essentially saying sports or class A has the highest probability for the given row, number one. Note that you always need to have the correct number of output nodes. What do I mean by correct number of output nodes is it should match the number of classes in your target variable. If you got politics, if you got sports, if you got uh, news, so you need to have three classes in your output variable that you define the algorithm with. You need to match the number of multiple class outputs in your classification algorithm with the number of different classes in the target variable. And only in this case, the algorithm is going to work correctly. All right. So you could use the same idea, but even with multiple classes, no hidden layer, one hidden layer, and multiple hidden layers. For multiple hidden layers, you will use the Keras library of the TensorFlow package. And if you do not have the hidden layers, you could use the scikit-learn, obviously. Again, softmax function assigns the probability for the prediction, and you need to have same number of output nodes as you got the number of classes in your target variable. Let's go back to see how the backpropagation algorithm really works. We already looked at this. This is just a summary. I initialize my weight and biases absolutely randomly. I send my first batch for processing. I calculate the error. I come back, adjust my weights and biases using the same idea as that of gradient descent. We looked at this before. Basically, we are making sure only those columns or predictor variables contribute to the final prediction who do who are contributing it correctly. Those columns which are not contributing to the final prediction or who are contributing negatively, making the final prediction go wrong, are reduced in terms of their weights and bias contribution. So based on the gradient descent, the same idea gets applied. As you incrementally run your iterations or batches, you update your weights and biases, reduce the contribution of those columns which are contributing negatively or which are not contributing at all, and increase the weights and biases of those columns which are contributing positively to the correct prediction. You don't want the incorrect prediction, obviously, and that's how your algorithm runs. So you send it in terms of batches, you adjust your weights and biases, then you send another batch with batch two, calculate its error, and repeat the same process. This whole thing becomes first iteration. And obviously, I told you iteration is called epoch in terms of neural networks. So you define the number of epochs, so you define the number of iteration. It could be 500,000 based on your computation power, and you improve your weights and biases, and that's how you freeze the model once your model becomes pretty accurate. These are a bunch of different activation functions. You have 10 hyperbola or hyperbolic 10 theta. It ranges from -1 to +1. We have ReLU function. Every time it becomes zero, every time the sum is less than zero or negative, this activation function always gives the output or always gives the y value of zero. Every time it's positive, then I have linear relation between x and y. Just going back, what activation functions are used for? Activation functions are like the threshold of the neurons. If the pain in your body is too high, then you got to step back and take your hand away. The same idea is with the activation function, mathematically speaking. If the value exceeds the certain threshold, if it's positive, for example, for this activation function, the output could be 1. If it's negative, the output is always 0. It did not exceed the threshold of positive summation, output is 0. All right? You are practically defining the threshold mathematically, the threshold that is biological in nature. Here you're defining with the help of these activation functions. And you could use any of those based on your demands and needs, and sometimes even hit and trial what works best for your data set. You could have a step activation function. Every time your sum comes out to be negative, it's again 0. Every time it's positive, it's always 1. And both these functions, step and ReLU, they don't have, or they are not differentiable at 0. It keeps the gradient descent algorithm bouncing around. But it still works well with ReLU, but it does not work quite as well with step. So we try to avoid this one, but we still use sigmoid, which ranges from 0 to 1. Every time your threshold, for example, exceeds, in this case, 6, you always have 1. If your threshold always exceeds -6, you always got 0 on my y-axis as my prediction. Or every time you have a summation that's in less than 6, let's say 2, you might go up to here and turn this way, and your y-axis, which is your prediction, might come out to be 0.8. You even have a leaky ReLU when you want to introduce like some y outputs when your values or sum is negative, and this is called leaky ReLU. Note that leaky ReLU, or ReLU for that matter, does not only range from 0 to 1, it could go from 0 to 10 and so on. It's a linear relationship between the sum and the output. Let's look at the neural network and the different libraries that are associated with them. Scikit-learn, TensorFlow. Scikit-learn is pretty good when we are dealing with just no hidden layer, and when we are dealing with hidden layers, either single hidden layer or multiple hidden layers, we could say that we want to use the TensorFlow library called Keras. You want to use the classifier, MLP classifier, when you have a classification task. You always want to use the regressor when you have the regression task. Different parameters or hyperparameters to train the scikit-learn at. Obviously, this is again a high-level API. You just define the basic API in Python and define a bunch of hyperparameters, and the rest of the background work, it takes care of itself in scikit-learn. Hyperparameters include how many hidden layers you want to define, We try to do the hidden layer deep network work using the Keras, not using the scikit-learn package. But you could also define the activation function, solver, penalties we discussed probably before. These are to reduce your overfitting problem. So this there we got L1 penalty, L2 penalty. But here we can use the L2 penalty learning rate. We could define what's my maximum learning rate going to be or minimum learning rate going to be. We can define the maximum iterations, how many iterations we want to do. All right. Similarly, we have TensorFlow. It's done through Keras. You could define your own deep neural network algorithm, but it's going to take more effort. But chances are you could use more hyperparameters or define it more customized to your data set that should run perfectly, learn perfectly based on your needs. But for general purpose, Keras does a pretty good job. All right, we can define the number of layers, neurons per layer, type of activation function. We looked at those activation functions. We can initialize, we can define the weight for initialization logic, learning rate, and so on. How do we fine tune the hyperparameters? Obviously, trial and error, it takes more time. You could use a grid search. You could define a range of parameters to play with, and it will run those range and give you the best parameters based on accuracy or any other um, criteria you would define. You could even use randomized grid search. So it will randomly check a bunch of different hyperparameters and give you the best algorithm or best accuracy hyperparameters through that grid search. All right, how do we define the number of layers? Mostly one hidden layer is adequate. More hidden layers if you want. You are expecting more computation power, more computation needs. But if you're doing like convolutional neural networks, you might need hundreds of layers. Mostly these layers help with image generation or image prediction. You want to learn from what this image is associated with. And that's probably what ChatGPT also uses. The challenge with more layers in regular data like classification and regression tasks uh, is you could lead to overlearning or overfitting. That test data, when you test it, the accuracy goes low or lower than the train accuracy. All right. So number of neurons, how do we define our how many neurons I want in a given layer? So input and output layers are predetermined. Input is simply based on how many columns I got, and output layers has number of neurons as the number of classifications within the target variable if it's a classification task. You can have hidden layers in two formats, funnel shape or pipe shape. Funnel shape would be like this. So your hidden layers, number of neurons keep reducing. So if you have like 6 neurons here, you might have 4 neurons here in the funnel shape, and you might have 2 here. And you could tell the algorithm, do the funnel shape for me, and it will take the initial uh, hidden layer count and develop the rest of the neurons based on the shape you have already defined. More neurons obviously might lead to overfitting. That's where funnel shape really helps. So you keep reducing the number of neurons. You can use L2 regularization to reduce the overfitting. You could use any other idea of early stopping. So if you reach a certain learning rate, you want the algorithm to stop learning and just hit a pause so that you don't overfit. Advantages and disadvantages. Advantage, obviously, performance. It's pretty accurate. It can handle very noisy data. Relationships between the output and input can be very nonlinear, no specific pattern, but it will still derive a pattern using the weights and biases. It will learn a lot of text. It will learn a lot of mathematical concepts. It will learn just about everything. It's able to learn information from images using those little weights and biases. Just about, so it can learn just about everything from your data. The patterns that you cannot recognize with your basic logical reasoning. But the disadvantage is it's a black box. It needs a lot of data to train it. It does not have like a very variable selection. It's very resource intensive. That's why only few companies have these learning models. Only practically just 4 or 5 companies in US and very few in China, because it takes a lot of computation power when you're trying to train like billions of parameters, train the algorithm based on billions of parameters or billions of nodes for that matter. It does not tell you the true nature of the relationships. this could be a disadvantage too. You cannot explain the true nature, how a certain word, how a certain data point is affecting a data point at a very far off distance based on different weights and biases, a complex network of webs that it has already created and frozen. You cannot tell those relationships that could be explainable. That brings me to the end, and I hope you enjoyed my presentation. And we're going to jump into some Python testing using Keras.